Now we're going to do the hard math of back propagation. So we'll come back here to these notes, and we have two key equations. One of them is for the partial derivative of the error with respect to the transition matrix, which is this formula, and the other one is basically this recursive formula. So why is this recursion equal to the definition of the sensitivity vector, which is that. So let's do this one first. Was that square enough for me to steal? I don't think so. All right, so I'll just copy it down here. So we want to figure out what the derivative of E with respect to WL is, and so we have this this formula, which is that this is equal to XL times delta L transpose. Okay. So the way we're going to attack this is we are going to look at the derivative of E with respect to just one single weight vector in this matrix. One element of this matrix, because this is just the respective derivative with respect to each of these elements. So if we can do this, then we can put them together to get a final answer here. So so we're going to use the chain rule here. So if you think about xj of L, so xj of L is all the inputs that are coming into node J and layer L. And so you can express this algebraically as, so Wij L. So these are the weights that are coming into layer L. There's going to be one of those for every output in the previous layer. So use this notation to describe the number of nodes in the previous layer, dl minus 1. And each one of those is being multiplied times the output of the previous layer. So this is output I here. Okay. So an observation is that E depends on Wij only through Sj. So, you know, as this process is going along, you have a certain node here, and then you multiply by WL minus 1 to get to the, let's just do WL to get to the next layer. Whoops. And okay. And then this gives you, and then you apply, you know, there's the S function. So WL goes through and becomes S before the layer L transition, and then you have the outputs from layer L after that. So the eventual function here, which we're trying to compute, which is the difference between theta of the eventual output and the label for this example squared, the only way the influence of this little weight becomes known is through this Sj. So all that you know, stammering and stuff is just to justify the use of the chain rule. So here I can express this using the Leibniz version of the chain rule as this is the same thing as the derivative of Sjl, derivative of E with respect to Sjl times the derivative of Sjl with respect to Wij L. Okay, So hopefully, with that might be strange, but that's just the calculus. That's just the chain rule from calculus 1. So you can sort of interpolate these the second variable in cases like this. All right, this is like U substitution. So both of these are easy to compute because from the definition, this one is just delta L, the jth entry. So this is just the jth entry of delta L by definition. If you come back up here, here's the definition of delta. So its jth entry is that. And now you have this part, but this part can easily be figured out just using using this expression here and your knowledge of calculus. So when I guess where here I is being used twice, but this is just going to be xi L minus 1. So what we've got here is dj L times x I L minus 1. Okay. So that is the derivative of the error function with respect to this single weight. And then if you put it all together in vector notation, it turns out to just be exactly equal to this. So if you take the outer product of x and delta, then the way these i's and j's work is just so that the i's and j's go in exactly the right place for computing each one of these for every, for the ijth entry in WL. All right, so that was the easy one. Now let's go on to the to this one, which is kind of the difficult one. So we'll start in a similar place. Can I copy this? I think so. So this one I can just copy and paste. All right. So the way we start with this is the simpler problem of trying to figure out what the jth entry of this thing should be. So what is the jth entry of delta JL? So this is by definition equal to the derivative of E with respect to the jth entry of SL. Okay, and so now we have kind of a similar argument about using the chain rule as we did before. So the error depends on SJL only through XJ. Because if you look at the network structure here, all these SJLs, by their influence on the output E here, it only goes it all goes through this XJL variable. So again, we can use the chain rule to write this as the derivative of E with respect to the output from node J and layer L times the derivative of XJL with respect to DSJL. Okay. So one of these is easy to compute, and it's this one. So you know that XJL is basically just theta of SJL. Okay. So when you compute this derivative, this is just going to be, this is a calculus 1 problem. This is just theta prime of SJL. Okay, so whatever that is, if this is hyperbolic tangent, then that's 1 minus theta squared. If it's ReLU, then it's something else. If it's ALU, then it's something else. But it's just theta prime, and all these thetas have simple derivatives. So that leaves, and you can see where that is showing up in the formula, right? It's showing up right there. when you put it back in the vector form. So the remainder of the story has to do with this thing, and this one is a little bit more complicated. We're basically going to do a similar trick. So here you have, if you look at this, if I change these, yeah, maybe I should just draw a different picture. So the output E, or the error E, it depends on XJL. So what is this? This is the output in layer L from the jth node, right? So here's the jth node in layer L, and then all of these copies of XJL go out emanating from this node, and then they get multiplied by their weights, and eventually they affect the inputs to the subsequent layers. So this would be, you know, SL plus 1, 1. This is S2, L plus 1, etc. So the thing that makes this case a little bit more complicated is that XLJ actually affects all of these S's. So it affects, here I'm just writing it like this, S1, L plus 1, all the way to S, you know, DL plus 1, that's the number of nodes in layer L plus 1, except that goes in the exponent. So here is, oh, sorry, oh, that was right, in layer L plus 1. Okay, so now all of these together affect the error. Okay, so what we have here is a failure to communicate. What we have here is a non-trivial case of using the chain rule, the multivariate chain rule. So if you've taken calculus 3, then you might just know that when a function depends on a variable through several intermediate functions, then you just you have to sum them up when you do the chain rule. So if you want to read more about that, then you can just Google multivariate chain rule, and the article that comes up will explain that better. But anyway, the formula that you come up with is the derivative of E with respect to XJL is the sum. This is going to be over all of the S's in the next layer. So we'll use K. So this is K equals 1 to DL plus 1, the number of nodes in the next layer. So now in each case, we just use the chain rule with one of those intermediate variables. So the partial derivative of E with respect to SK L plus 1 times the partial derivative of SK L plus 1 with respect to XJ L. All right, so the good thing now is that each one of these is easy to compute. So this one is just the kth entry of delta L plus 1 by definition of delta. So this is the kth entry here. And this one, if you think about it, here you just have all these weighted inputs, right? So the kth one here, what's coming in here that's relevant is just WJK, so that's the weight that connects J to the kth node over here, times XJL. So if you take the derivative with respect to XJL, you just get WJK. So this part just becomes WJK L plus 1. Right. And okay, so now we have that this is equal to this sum where you're adding up wjk L plus 1 times delta k L plus 1, and this is just as k goes from 1 to dl plus 1. All right, so if you put all of this stuff together, remember there were two parts. This was the hard part, which we've just been working on, but there was also this easy part, which we finished a while ago. So this whole thing can sort of be summarized. So delta L j is equal to theta prime of S L j times the sum as k goes from 1 to the number of nodes in the next layer, wjk L plus 1 times delta k, so I should be putting the bars on the delta, L plus 1. Okay, all right, so that is the jth entry. And now if you just figure out what this is in terms of the entire vector, it turns out to exactly be, this first part is easy, so this is just, you drop the j here. And then if you take, has to be respective multiplication, and then if you put the L plus 1, delta L plus 1 here, then this other stuff works out exactly right. All right, so in the first video we showed, how to use backpropagation to train the network, and here we've just proved why it actually works. So that's why this process, those formulas in this process compute the gradient of the error with respect to the weights. So that's it.